Hello and welcome. Suppose I have a signal x of t, then the time derivative of this signal is written as ddt of x of t. Now we shall use a shorthand of this notation, which is as x dot t. This dot denotes the time derivative of a signal. Similarly, the second derivative, which is d2 dt2 of xt, that can be denoted as x double dot t. Similarly, third derivative will have 3 dots and so on. Now imagine some signal x of t which looks like this. This is a piecewise linear signal. Now if I differentiate this signal with respect to time, I shall get something like this. X dot. So in this region the derivative is positive and has some value. Next, within this region the derivative is still positive constant but has a lower value. Then in this region the derivative is negative, like this. So this is how the derivative of xt looks like. Now the meaning of this derivative is rate of increase of xt, and if you integrate this signal, say within a region from t equal to a to t equal to b, then the area under this curve, so this area signifies the amount of total change or total increase of xt, this signal, original signal, between t equal to a and t equal to b. So between these 2 points the total change is this much, and this height will be same as the area under this region. Now yesterday we talked about a ramp signal which looks like this. It is 0 and then increases with an angle of 45 degree. If you take the derivative of ramp signal, unit ramp signal, that is r dot t, then we get u of t, unit step function, which looks like this. It is 0 before time equal to 0 and after that it is 1. If you take another derivative, which will be the r double dot t, That means the first derivative of ut, that is same as delta t, the unit impulse function, which looks like this. It is 0 almost everywhere except at t equal to 0, we indicate with the arrow. And this signal delta t is defined in the following way. Delta t is equal to 0 if time is not 0 and the integration of delta t dt from minus infinity to plus infinity, or within a narrow region surrounding this t equal to 0, that is from 0 minus to 0 plus, this integration or the area under the curve is 1. So this is the definition of delta t. Now you should observe one fact, that this integration from 0 minus to 0 plus, so 0 minus is a point very close to 0 but slightly before that, and 0 plus is a point slightly after the origin, and this integration can be written as u of t evaluated at 0 plus and 0 minus, because the derivative of u is delta t. So this is then equal to u of 0 plus minus u of 0 minus, which is same as 1 minus 0 equal to 1. So this justifies the definition of delta t. Now let us solve some problem. So here is the question. Some signal xt is given to us and the question is to draw x dot t. Okay. How do we do that? Observe that in this part xt is constant, so the derivative will be 0 here. So the derivative is 0. So this is x dot t. Now within the region from 0 to 1, the signal increases at a slope of 1, so the derivative here will be constant and equal to 1. Then from time 1 to time 2, the signal decreases with a slope of -1, so in this region this signal will, the derivative will be -1. Then after that from 2 to 4 the signal is constant, so the derivative will be 0. After that again the signal is constant, so the derivative will be 0. So this is the derivative of xt, but this is not correct. This is wrong. Why? You can verify that this is wrong by back calculating. That is, you start from this derivative and integrate this signal and check whether you get back the original xt or not. So let us do the back calculation. Let us start from 0, and then here the rate of increase is 0, so the integration will be flat. So I am drawing x of t back calculated from x dot t. Starting from 0, in this part the signal xt will not change. After that, in this part the signal will increase at a slope of 1, with a slope of 1. So it increases like this. Then between 1 and 2 the signal should decrease with a slope of -1. That is like this. After that the derivative is 0, so the signal should remain constant. So this is the back calculated xt, and is not similar to original xt. Therefore this calculation is wrong. Why is it wrong? Because we have to consider these step jumps. So we have a step jump here, another step jump here, another step jump here. So we have to account for these step jumps. What we need to do is as follows. Anytime you have a step increment, you have to add in the derivative a delta function like this. So here I have a step increment of an amount of 1, 0 to 1. So I shall add a delta function, delta of t, with height or with strength equal to 1. Then here I have a step decrement. So here again I have to add a delta function, but this time the delta function will be negative because it is decreasing. Also the amount of decrease is 2 units from 1 to -1. So therefore I shall draw a delta function with double strength. So this will be -2 delta. Minus because it is in the negative direction, 2 because the total change is 2 unit, and delta of t, not t, rather it should be t minus 2 because it is shifted from origin. So we have to incorporate this time shift. Next, consider this step jump here. Again we have a step increment. So at this point we have to add a delta function positive, and the strength of this delta function will be 1 unit, because here the change is 1 unit, and this I shall write as delta t minus 4, because it occurs at time t equal to 4. So this is the correct derivative. Now we have defined unit step function, which looks like this: 0 here and then 1 here. This is u of t. Now I can ask, how will the signal u minus t look like? Let us draw this signal. Time now this is a time reversal of the original signal. Therefore, this signal will have a value of 1 before t equal to 0 and then 0 in this region. So this is a time reversed or horizontally flipped version of this signal. Then I can ask you that how will the signal u t minus 1 look like? Let us draw that. Time versus the signal u t minus 1. This is a time shifting. So you have to shift this signal by 1 unit towards the right. So that will look like this. It will start from here and then continues like this. Before that it is 0. This is t equal to 1. Now I can ask you, how will the signal, say, u t minus u t minus 1 will look like? Let us draw this signal. To draw this signal, you have to subtract ut minus 1 from ut. Now if you subtract this and this signal, then the difference will be 0 in this part. After t equal to 1, this is 1, this is also 1. So the difference here will also be 0. But in the region 0 to 1, the difference between this and this will be 1. Because this is 1, this is 0, 1 minus 0 is 1. So this is how this signal will look like a box. This is sometimes called a gate signal. Now let me ask, how will the signal, say, r t minus 1 and then a minus sign, how will this signal look like? Let us try to draw. Time versus minus rt minus 1. Now you can start from the signal r of t, this is how r of t will look like. Then because of this -1, you have to shift the signal towards the right by 1 unit. So if this is t equal to 1, then you shift it by 1 unit, and this is r t minus 1. And then finally, because of this minus sign, you have to invert or flip this signal vertically. So that will be like this. So this is minus r t minus 1. Before this it is 0 and this angle is 45 degree. Now let me tell you a very interesting fact, that any piecewise linear signal, that means signal which is composed of small straight lines, so any such signal can be written or expressed as a sum of step and ramp signals. Let us understand this fact with a small example. So here is an example. Suppose we are given a signal xt, arbitrary but piecewise linear signal like this, and the question is to express this signal xt as a sum of step and ramp signals. So this is the question. How do we solve this? We shall start from the left side of this signal, and from the left side you observe that this signal looks like a ramp signal. It is initially 0 and then increases linearly. So we can write that x of t is equal to our ramp rt plus some other components. But xt is not same as rt. Why? Because if I draw rt, that looks like this. It increases forever. It continues to increase forever. However, xt stops to increase at this point and becomes flat. So this is rt, and rt is not same as xt. Now I can add another signal with this, which is as follows. That signal is initially 0 and then at t equal to 1 it starts to decrease like this. Okay, so this is t equal to 1, 2 and so on. This angle is 45 degree. Now if I add these two signals, then I shall get the following. The result of addition will be 0 here, then if you add this and this, then it will increase at an angle of 45 degree up to time t equal to 1. After that, this signal continues to increase with a slope of 1, and this signal starts to decrease at the same but opposite or negative slope. So this increment and this decrement will cancel each other, resulting in a flat signal like this. So this is the result of adding these two signals. But this is still not same as xt. So we shall add one more component with this signal, and that will be like this. It will be 0 from minus infinity to up to the point t equal to 2. After this point, it should go down and become equal to minus 1. So if I add this signal with this signal, then the result will be as follows. When you add this and this up to this point t equal to 2, the result will be same as this signal because this is 0. So up to t equal to 2, it will be like this. One, 2. After this point, this has a value of 1 and this has a value of minus 1. When you add these two, result will be 0. So it will come down and become 0 forever after. And this signal looks same as xt. Therefore, I can write xt as a sum of this plus this. Now can you recognize what is this signal? This signal is nothing but r of t minus 1 and minus of that. Can you recognize what is this signal? This is minus of u t minus 1. Therefore, I can write xt as rt plus minus rt minus 1, which is this signal, and then this one, which is again minus u t minus 1. So this is the answer. And this way you can express any piecewise linear signal as a sum of ramp and step signals. My mistake. Here it should be t minus 2. And here as well t minus 2. Now we shall take a break and look back and revise what we have learned yesterday. So let us recall some important properties of an impulse function. Number one, I can say that delta of 2t, it was equal to delta t divided by 2, because delta 2t is like, if I first draw delta t, if this is delta t zoomed in, then delta 2t is a narrower version, squeezed version. So the area of delta 2t is half than the original area of delta t. That's why we can write this. Then if I write delta minus 2t, then that will be same as delta of plus 2t, because this is a time reversal because of the minus sign. However, if you flip this signal horizontally around t equal to 0, nothing changes. The signal remains still at the same position, same location, and the area is also not changing. So these two signals are same, and which is equal to delta t by 2. Therefore, in general, I can write delta of kt, where k can be positive or negative, any number, that should be equal to delta t divided by modulus or absolute value of k, which you can verify from these two observations. Next, very important property, xt times delta t is same as x0 times delta t. Next, if I write xt multiplied by delta t minus some number constant a, so time shifted delta function, then this is same as x of a multiplied by delta t minus a. From these two properties, I can also write that the integration of xt delta t dt, that is this term, if you integrate, that will be same as this term integrated, that is equal to x of 0 minus infinity to plus infinity. Then similarly, look at this expression and we can write x of t delta t minus a integrated from minus infinity to plus infinity. This gives x of a. Next, we are going to learn a very important fact about signals. Suppose a signal is given to us, any arbitrary signal, call it x of t. Now let me divide the time axis into small segments. This is t equal to 0. Call this time t equal to delta t. Then this time is 2 delta t, 3 delta t. On the other side, minus delta t, and so on, such that delta t is very small as you can imagine, tending to 0. Now the value of the signal xt at this point can be written as, say, x of 0, at this point x of delta t, here x of 2 delta t, and so on. So this is the height, these are the heights of xt at this particular node points. Now what I can do, I can approximate this original signal as a piecewise constant signal, which looks like this. Say in this region, I shall approximate the signal as a constant like this. Then from here to here, I will approximate as a constant signal like this. At this point, another constant signal like this. Here, another one like this. So this way, then we can join these parts, and this is how the piecewise constant approximation of the original signal looks like. Piecewise constant approximation. Okay, call it x tilde t. Now, if you choose delta t to be very small, that is when delta t is tending to 0, then x tilde t and xt are same. Then there will be no difference between this approximation and the original signal. Next, we can write this approximate signal as a sum of a number of gate signals. Let me show that. Let me first draw a number of axes. Now look at this part of the signal. From here to here. So this part I shall draw like this. Okay, so this signal is representing this part. Then consider this part, which I shall draw here. So this part is representing this part of the signal. Next, consider this region where the height is 1, 2, 3, 4. So I draw it like this. This is same as this region. Now, if you add all these signals, this plus this and so on, all other parts corresponding to this region and so on, if you add all of them, then that will result into x tilde of t, this red colored signal. Okay, so therefore I can write x tilde of t as a sum of all these signals. Now we need some mathematical expression for this signal and this signal and this signal, so that I can write it here and add them up. So what should be the mathematical expression for this signal? Note that when delta t is close to 0, then this is like a impulse function, because this is 0 everywhere other than a very narrow region near t equal to 0. So this will look like a impulse function or impulse signal delta t. However, the area under this curve is not equal to 1, but it is much smaller, because the height of this signal is not infinite but much smaller. So it will be an impulse signal but not unit impulse signal. It will be a much smaller impulse signal, so which we shall write as delta t multiplied by a very small number, which will represent the area under this curve. Now how much is the area under this curve? Let us calculate the area. The area will be equal to the height of this signal. And how much is the height? The height, we have written it here. Here this height was x0, and therefore this height is also x0. So x0 is the height multiplied by the width. Now how much is the width from here to here? So that width is this width from here to here, and you can see that this is equal to delta t. So this is the area. Okay, so this factor should represent the actual area under this curve, and that is x0 times delta t. So this is the area. So this represents this signal. Similarly, to represent this signal mathematically, you note the height of this signal is same as this height, which is x of delta t. So height is x of delta t, because this point is delta t, this height is x of delta t, and the width from here to here is same as delta t. So this is the area. And once again, when you consider delta t to be very small, so you chop or slice this signal into small slices, then this will be a very narrow spike like a delta function with this much area. So this signal can be written as this number multiplied by a delta t, not delta t, rather it should be delta t minus this delta t, del t. Okay, do not confuse with this capital and small delta. This should be t minus del t, because when you shrink this into a narrow pulse, that pulse is going to occur at this point. Now, can you tell what should be the expression of this pulse? It is occurring at the point 2 del t, 0 del t and 2 del t, and the area of this curve will be this height. This height is this height, which is x 2 delta t multiplied by the width, and then delta impulse of t minus 2 del t. Thus, this x tilde t can be written as a sum of, let me first write it this way, this signal x0 delta t times this plus this signal, which is x of this delta t delta t minus del t plus this signal, which is x 2 delta t del t minus 2 delta t, and so on. You also have to add the pulses corresponding to the left side of t equal to 0, this pulse, etc. So this sum will continue on this side as well. And then in a compact form, I can write it as a sum of x. This you see varies as 0, del t, 2 delta t, 3 delta t, and so on. So I will write as n times delta t. Sum will be carried over the integer n. Then we have this term common everywhere. Then an impulse function delta t, here we have t, here we have t minus 1 delta t, then 2 delta t, and so on. So this I shall write as t minus n delta t, and we have to sum over n starting from minus infinity to plus infinity, all the integers. Here you see we have n equal to 0, 1, 2, 3, 4. On the other side we will have minus 1, minus 2, which we have not written. Now you know that the original signal x of t is same as the approximated signal when the limit delta t tends to 0. So we can write this original signal as the limit of delta t tending to 0, x tilde t, which is this sum. Let me write this sum, x of n delta t, then let me write this term first, delta t minus n delta t, then this term delta t, and sum is taken over n equal to minus infinity to plus infinity. Can you recognize what this sum actually means when this interval is very, very small? According to Riemann, then this sum will become integration. So we can write that this is the integration of x of, in place of this n delta t, let me write some variable, call it tau. Then delta t, once again in place of n delta t, I shall write a dummy variable tau, and this will become d tau. So this summation is same as this integration over tau, and tau running from minus infinity to plus infinity. So this result is very important. Let me write it freshly once here. Any signal x of t can be written as the integration of x tau delta t minus tau. The integration is carried over tau. Tau is a dummy variable which runs from minus infinity to plus infinity, and when you carry out this integration, tau will vanish and it will be a function of t only. So this is a very important result. There is a simpler way of proving this formula quickly and mathematically that I shall show you. Quick proof. We already have proved once. Another quicker proof. Start from the right hand side. This integration. X tau delta t minus tau d tau from minus infinity to infinity, and then apply a change of variable, put t minus tau equal to z, such that delta tau d tau is equal to dz. Then the RHS, right hand side, can be written as x of, in place of tau I can write t minus z delta z. I have missed a minus sign here. Then put a minus dz, and the integration will run from plus infinity to minus infinity. Z equals plus infinity to minus infinity. Okay, and then this is same as, now what you can do, you can use this minus sign and change the range of, or the limit of integration, make it minus infinity to plus infinity, x of t minus z delta z dz. And now you recall the formula that we have learned, that any function, say y of t multiplied by del, or let me call it z, y of z multiplied by delta z integrated from minus infinity to plus infinity is same as y of 0. So what you do basically, you put 0 in place of z in the expression of y. Okay, so now if we do the same thing here we have delta z, assume this to be yz. So what you have to do, you just have to put z equal to 0 in this expression, so it becomes x t minus 0, or same as x of t, which is the left hand side. This is a quick way of proving this formula, very useful. We will need it again and again, but the physical meaning of this formula is what we have demonstrated here. Any signal can be broken into a sum of delta signals, impulse signals. Let me write this fact. Any signal can be expressed as a sum of impulse signals, like this, sum of time shifted impulse signal you can call. Now let us now talk about systems. Yesterday we said that anything which has one or more inputs and one or more outputs and some relation between the input and output can be considered as a system. Now while drawing a system, we shall draw it like a box. Any system can be drawn like this. We shall put an arrow pointing inward to indicate the input to the system, and we shall put an arrow pointing outward to indicate the output from the system. In this course, we shall consider systems with only one input and only one output. Now, input can vary with time, so input is a signal which you may denote with the symbol xt. Similarly, output can vary with time, so output is also a signal which you may denote with the symbol yt. That's how we draw a system. Let us now look at some simple examples of systems. First, let us consider say any object kept on the floor, and this object is my system. You can apply a force on this object, call it f of t, that can vary with time, and this is the input to my system. As a result, this object will have some acceleration that we can consider as the output. call this A of t. Now the relation between the input and output in this case is very simple. We know that F of t is equal to the mass times A of t. This is the output, this is the input. Now if you like, instead of considering acceleration as the output, you may also consider the speed or velocity as a function of time as your output. You may also consider the position of this object on the floor as your output. Depending on your requirement and the situation, you may choose any of these as your output. So this is one example of a very simple mechanical system. Now let us consider another example, which is a piece of resistance with value R. You can apply a voltage across this resistance. Let me call this voltage as the input and denote it as V of t. As a result, we shall get some current, and that we can call as the output I of t. So this resistance is a system, and the relation between the input and output is very simple. I of t is equal to V of t, the input, divided by a constant resistance. Let us consider another simple example, which is a coil or a piece of inductor. Let it be a pure inductor, and through this coil you can pump in some current, call it I of t, and let this current be considered as the input. And as a result, there will be some voltage induced across this coil, call it V of t, and that is the output. Now the relation between the input and output is very simple. We know that V of t, voltage, is equal to derivative of the current ddt of it multiplied by some constant L, that is the inductance. So these are some electrical systems, very simple. Now let us consider another system, which is a container containing some water in it. Which is kept on top of a heater, on top of a water heater. The heater has a coil, and if you pass current through this coil, the heater will heat up the water. Let me call the current which flows through this coil as the input to this system, call it IT. This is the current which is the input, and let me put a thermometer inside this container, and the reading of this thermometer, that is the temperature, can be considered as the output from this system. So this is an example of a simple thermal system. Once again, you can find out the relation between the output temperature and the input current easily, we may write that the rate of change of temperature ddt of temperature multiplied by the mass and the specific heat of water, that should be equal to the heat inflow, which should be equal to the current I square multiplied by the constant resistance of this coil. This is true under simplified assumptions like that this entire system is insulated and there is no heat leakage, etc. So that was a simple example. Now let us consider another simple system, this time a hydraulic system. We shall consider a water tank which has an outlet. So this is a water tank, and it also has an inlet. So you can pump water into the water tank, and you shall also get water coming out from the outlet. Let me call the flow rate into the tank as Fi of T, amount of water flow per unit time, that is my input, and the amount of water flow that comes out of the tank, let that be the output. This way, this is a system. We can again find the relation between the input and output easily this way. If I call the height of this water level as H, H of T, then we know that water flow rate outward, that depends on the pressure of the water, which depends on the height. So I can write this as some constant K1 times HT. Now the height of the water changes depending on both the input and the output flow rate. We can say that the rate of change of the height of the water is some constant K2 times the flow rate inward minus the flow rate outward. Now we can combine these two equations. For that, let me replace this H in this equation, that I shall replace with FO divided by K1. So FOT divided by K1, and this is equal to this part, which is K2 times FIT minus FOT. So this is the relation between the input and output of this system. Here I have a paperweight hanging from an elastic rubber band, and this is a system. If I raise my hand upwards, then this paperweight is also raised upwards. Now let me call the position or height of my hand with respect to this horizontal line as the input to the system, and the height or position of this paperweight from this horizontal line is my output. At this moment input is 0 and output is also 0. Now if I increase the input, output will also increase or change. Let me plot the graph of input as a function of time and the graph of output also as a function of time. For that, let me play this video at a slower rate. Currently the input is 0 and it is 0, 0, 0, and then at this point the input is increased quite fast and then it is kept constant afterwards. So this is how the input signal looks like. Similarly, initially the output is 0 and it continues to 0 until I give the input, and when I give the input at this point of time, then you shall see this paper weight goes up and then comes down and then goes up and down and up and down, and it oscillates for a while and finally it settles down to a height which is here. This is an example of a mechanical system with one input and one output. So these simple examples should give you some idea about what we mean by a system. When you master all these simple systems, then you can analyze complex systems like aircraft, missiles, etc.